Hello, everyone. Welcome back to the AAS YouTube channel. And this is the ebook series. And I'm super happy to have Andrei Mesinger with us today. Hey, Andrei.
Hello. How's it going?
I am doing well on this June 25th on a Friday.
Same here.
Where is here for you? Where are you located at?
I'm in Pisa. I'm at Scuola Normale Superiore, which is a high-level institution in Italy, Pisa. So it's a beautiful summer day here.
Oh, lovely.
Enjoying the summer.
Very lovely. Let's see. We are we're actually a little bit on the cooler side in Phoenix today. So I'm in Phoenix. Typically in June, July, August, which is the wet season in Phoenix, we'll get up into the 43, 44 Cs.
Oh, wow.
Oh, yeah, we toast. We toast.
That's hardcore. Here's Mediterranean. We kind of typically stay below 30. So you can, and then there's a nice kind of cooling in the evening. So you can go to the beach. The beach is 20 minutes away.
Oh, lovely.
And go to the beach and hang out a little bit, and then in the evening it cools down. So it's pretty moderate.
I'm gonna have to come visit you in Pisa.
You should. You should. It's a popular. It was.
Oh well,
a year and a half ago when something happened that shall remain nameless. But yeah.
Yes. Well,
it'll pass. Yeah.
These things will pass. Very cool.
Yeah.
So Andrei, what do you like to do for research?
So I like to study the first billion years of the universe, as we like to call them. So this comprises the birth of the first structures, the first galaxies, the first stars, the first black holes, the ancestors of what we see around us today, and in some ways us, if you want. And so these first billion years in time speak, given that the universe is 13.7 or so billion years old, might not seem too much. It's the infancy of the universe. But if you look at the total volume that is kind of probed by these first billion years, it's actually the majority of our light cone. So if you're looking for where the future of astronomy is going to be, I would say the future is in the past, because it's difficult to see out to those distances. But that's where the information is. That's where the majority of our light cone is sitting there. And so, it's an exciting time, I think, to work in this field.
Yeah, absolutely. And I do have to comment. I love that board behind you there. That's just
awesome. Thanks. It's pretty organic, as I never really erase it, so I just kind of erase a patch when I have a student come in, and I work in certain patch, so you can see different colors when different times. There's some 21 centimeter Lyman alpha stuff, and then just random gridding simulation stuff. So it's really a hodgepodge.
Very cool. And that is going to bring us to this super lovely, fairly new ebook. As soon as I find it. Sorry about that. Where am I here?
Did you pay the copyright?
I did.
Good.
I know.
I don't get any money from that, so.
Yeah. Speaking of, so let me ask that. So the Cosmic 21 centimeter revolution. So how did this ebook come to be? What gave you the idea to do an ebook, and roughly, from start to finish, how long did it take? About 2 weeks, maybe?
Yeah, right. I wish. So, I mean, I was kind of informally approached by some editors and to saying this was kind of a hot topic, and would I be interested in this? And it is. It's a really, really burgeoning field. Like I said, it's the future, and it's something I've been involved in the past decade of my research. And so I thought it was opportune to put together a nice reference for people that are working in this field, or even starting out in this field, that they can go and they can look in, chapter blah, if they want to see how to, derive or deal with certain relevant things, and put it all together in one place that's reasonably easily accessible. It did take a while from the kind of planning of what chapters to have, and then soliciting the experts to write those chapters. I'm just the editor here, so the chapters were written by a mix of global experts in each of the fields, and so this, it took a while getting drafts and reading it, and then getting comments and different iterations and
2 years
so
maybe?
forth. So yeah, I think overall it ended up being close to 2 years from start to finish. Yeah. Yeah.
Seems to be a common.
It's between, I think, 1.5 years and 2. Yeah, it's always longer. Everything is longer than you think. Yeah. And there are times where you feel like you're shepherding cats. I love that expression in certain ways, but overall, I can't complain. The authors really did an amazing job, and stuck to the deadlines for the most part.
And speaking of, let's see if we can give a shout out to those folks. So there's the editorial board, 21 centimeter edited. And let's see. Well, maybe you can just give a shout out to people as we walk through maybe some of the chapters or what the high level.
Sure.
See them immediately. Let's see if we get them.
It should be below. Yeah, right there.
Oh, there we go. Let's give a little shout out to some folks.
Yeah, so we have Gianni Bernardi, Emma Chapman, Steve Filanetto, Lincoln Greenhill. Well, you can see from the field, but from the list here, Bradley Grigg, Vibor, Jordan Miroka, Jonathan Pober, Ravi, and Kath. I think the nice thing about this group of people is that a majority of them all of them are very active in the field. So they're not, writing memoirs. So to speak, they're involved
in professionals.
Exactly.
Yes.
So that's something that you need for something that is going to be, like I said, a reference. And part of it invariably is going to age out because it's a burgeoning field as we get more data, more stuff. But then we also have the kind of fundamental theory and general design of telescopes that is kind of something that should be timely.
Timeless, man. Yeah, and we'll loop back to that at the end if there will be a 21 centimeter version 2 in, let's say, a decade or so.
Sure.
But anyway, why don't we just walk through sort of what's in the ebook, and so maybe just walk through a little bit through the table of contents or so, and we'll go wherever you want to go. Looking at
sure. I thought maybe we could start from the figure of the light cone, just to describe what is the signal that we're talking about.
Okay, so 226, yes.
Yeah.
We looked at that. 226, 210, 20. Love all those equations. 226, and there we go.
Yeah. So this is just kind of showing the potential kind of visually of this probe, the 21 centimeter probe. So I spent, I've been working in this field. I got my PhD in 2006. So I've been working in this field for a while, and most of my time has been kind of working to understand probes of reionization, which is this process where the most of the universe was ionized. It's the last phase transition, the last interesting thing to happen to all of the baryons. And we're working on it to study with upcoming and current data, and trying to kind of isolate like what stage of reionization we're at a given time. And so we're basically kind of populating like this curve of the evolution of reionization versus redshift. And really, this is going to be a game changer, the 21 centimeter signal, because we're no longer talking about like understanding, one function. We're talking about getting, a three-dimensional map of the universe and of the first billion years of the universe, and looking at these beautiful structures that can span almost the entire first billion years. And so if you go from the right side of this figure, towards the left, you can see time increasing, and there's a time axis on the top. But like this starts from almost 20 megayears after the Big Bang, before there were any stars, there were any galaxies, anything. But through the 21 centimeter signal, this is the spin flip transition of neutral hydrogen, we see fluctuations, this kind of structure in the universe, and below it you see kind of the average signal and the power spectra. This is what interferometers measure below that. But you see these fluctuations from the different densities as the nascent structures forming, the different overdense regions grow and gravitationally. And you can see this beautiful structure. This is far future because it's difficult to observe at those frequencies. But then as you move on, at a few hundred million years after the Big Bang, the first galaxies and stars form. And there you see how their light impacts the intergalactic medium. And you see the timing and the structures that are here correspond to how stellar light permeates the universe. And does something called Wilthausen field coupling. And then you have heating, which is sourced by black holes. And that's the next phase that's shown here at around 300 megayears. And again, where black holes are distributed in our universe is kind of sources these maps. And the structure that you see here. And then finally reionization, when we stop having a signal because the universe becomes, well, for the most part, the universe becomes ionized, and most of the signal goes away because it's sourced by neutral hydrogen, as I said. And so you can get this beautiful dynamic range that you see in the colors here, and kind of it'll transition us from being a data-starved field to being really a big data-rich field. So I think the potential is quite significant.
Cool.
So yeah, so we can, I don't know if you want to, well, we can show also the movie of this version. This was a simulation. I should stress that, this is one simulation of something that we don't really know what's out there. So the exciting part is that we don't actually know. And so it could be very different from what is shown in that figure.
Let's see, which one do you want? This one?
Yeah, we can just show, this is just a 3D volume rendering of the dawn of the galaxy part that you see here going through one of these simulations. So you can see how these structures are imprinted in the gas. This is about, I think, 4 degrees on a side. So you can see how that goes from these different heating and then ionization and various astrophysical epochs. And these structures actually tell us about the galaxies and the black holes that we actually don't see. We don't see it even with the most powerful telescopes. We won't see them, most of them, with even JWST. But those patterns that you see in this movie, they tell us their star formation properties, what kind of black holes are sitting in them. They tell us a lot about them without actually directly seeing them, but how the radiation fields influence the universe, if we can encode this.
Nice.
So that's the kind of potential and the kind of motivation of I think the field. And maybe we can go through the chapters now to get an overview of what's in the book.
Absolutely. Thank you for that intro. For that movie.
Sure.
All right, let's get to the chapters. There we go.
Yeah, so this is the table of contents. We try to be systematic and kind of include the major pieces of the puzzle. And so we start with the theoretical framework. These are the physics of the line, the small scale quantum mechanical processes that are, and radio transfer processes that are responsible for setting the signal. As it says here, radio transfer, and then the spin temperature, which characterizes the level populations in the excited and de-excited states, and what are the responsible physical processes for setting the spin temperature. And then in the second chapter, we move on to the radiation fields. So the first chapter is the fundamentals. The second chapter is how stars, galaxies, black holes drive the radiation fields that are responsible for these processes that are shown in the first chapter. And so you see here sources of UV X-ray background. As I mentioned, you know, stars, indirectly stars are responsible for everything. Even black holes were once stars. In most theories, let's say, without going into details.
That was nicely said.
You have to add caveats, little footnotes. You know, there's dark stars and various other. But yeah, in the standard picture, stars are sorry, black holes were once stars, and so everything starts from stars, is what I was saying. And so how stars forms, what are their typical spectral energy distributions, what black holes they leave behind, these kind of things, how they interact with their environment, how they interact with neighboring galaxies. These kind of things all determine the different radiation fields that are going to be responsible for the signal. So that's described in this chapter 2. Essentially what we can learn astrophysically, and then chapter 3 discusses what we can learn about physical cosmology. So what about fundamental cosmology? Things like you know, just looking at the matter power spectrum or the matter structure in the universe. Things like redshift space distortions could also be probed. Baryon acoustic oscillations, or in this case, they're velocity acoustic oscillations. This intrinsic characteristic scale that tells us about cosmology, and potentially that could be probed. Exotic heating processes like dark matter annihilations, and various other physical things that can be probed. That's in chapter 3. And then chapter 4 deals with, so now we've established, you know, what we can learn. Chapter 4 deals with how do we actually learn that. And so in addition to having kind of the theoretical toolkit, identifying what are the different pieces of the puzzle that we can learn, we have to actually quantitatively, you know, confront our models with the data. And that's essentially what chapter 4 does. So you basically need some way of taking the data, summarizing it in some way. The common approach is a power spectrum statistic, but here you see a bunch of other statistics, and then using some kind of forward modeling approach or some way of comparing your theory to the data to be able to draw quantitative conclusions. And I send you a movie that shows this process that's characterized.
You want to take a look at that now?
Yeah, I think maybe that's a good time. So this is
okay. Which one was this going to be? This not must be the second one. The other one.
Yeah,
this one.
Yeah. So here you see this. It's a busy plot, so I'm not going to go through all the panels. But basically, it's one of these MCMC samplers where you see in the bottom left, you see a bunch of galaxy properties. These are parameters that characterize galaxies. And then on the upper corner, you see a bunch of observations, including a mock, because we don't have one 21 centimeter one in the top. And then the sampler essentially explores all of the different theoretical models that we have, the parameters that characterize our models, and compares it to the data. In this case, the data is the power spectrum that's shown in the middle panels here. And if you run the movie, you can see how these models kind of start converging, and they find the correct answer. They find the mock observation, statistically characterizing it in terms of the unknown properties of galaxies. And in this case, the mock observation corresponds to something that we expect from the hydrogen epoch of ionization arrays, which I know you're familiar with. And so this is a forecast of what we'll get after 1,000 hours of observation with Hera.
Pretty good.
Yeah.
Pretty good. Very nice. Speaking of Hera, want to show some zoom-ins to telescopes?
Sure. You can see Hera. So Hera is NSF funded and by the Gordon and Betty Moore Foundation funded telescope. It's led by international collaboration, mostly from the US, but a lot of international support. And it's actually, it exists. This is not a mock-up. This is a movie that Josh Dillon made, who's a Hera collaborator, from using Google Earth. And you can see a zoom in on the actual dishes that are sitting there. So it's almost fully complete. It's been taking data. We're analyzing that data. So it's on that threshold of current and future experiments. And then ultimately after that, we'll have the square kilometer array, which is yet to be built, but that's going to be, this instrument is optimized for getting a power spectra. So the statistical signal that I showed in the previous movie, getting that power spectrum measurement, the next generation square kilometer array will aim to make an actual picture of a three-dimensional picture. And yeah, so that will be.
So let me ask, why this location? Why not anywhere else?
Well, so one of the things, and that's in one of the chapters, is one of the things that's a problem are foregrounds. Actually, the main thing that's a problem are foregrounds. And one of the foregrounds that we have are what are called RFI, radio frequency interference.
Okay.
And so you want to build radio telescopes far away from people because people make noise. Radio waves, they make noise. We get noise in a bunch of bands, but a lot of these can be excised if there's some satellite that's coming overhead at this time, you can cut out that piece of data. So but if you're sitting in a city, then there's just noise all the time, all over the place. For the most part. So they're usually in deserts. Telescopes. So yeah, so going through it further, so I did 4. 4 was after we say like, what can you learn? 4 is how do you learn it? So introducing the statistical methods that we have to kind of do inference about the astrophysics and cosmology. And then we move on to the observational aspect of this. And in chapter 5, we have a very nice intro to interferometry. So even people that are not in the field, they can go and they can see how an interferometers work, starting from a two element interferometer, moving on to multiple elements, and what are the kind of the strategies for designing interferometers. And then in chapter 6, we discuss foregrounds, which we just mentioned. One of them is RFI. The most scary one for this measurement are galactic foregrounds, synchrotron from our galaxy. And so this is something like 3 orders of magnitude brighter than the signal we're after. And so we really have to characterize them in some way to a very, very high precision. And so this deals with how what are the foregrounds and how we can potentially mitigate the foregrounds, how we can either look in a different region of kind of our data space where the foregrounds are not so dominant, or just kind of remove them through better and better mitigation strategies. This is currently the biggest challenge is as if you look at how the data is coming, we have upper limits, and as kind of we get better and better at removing foregrounds, understanding foregrounds, these limits are coming down, And so, you know, we're getting closer and closer to where we think the signal is.
Cool. Awesome.
And then this chapter 7 is about the global signal. What is the status of global signal? Global is a sky averaged signal, as opposed to an interferometer that looks at the differences between patches in the sky.
Okay.
And so there's a status of some of the active edges, which you should also be familiar with. Had a claim of a detection, and there are also SARAs and LEDA, some of the global instruments that are currently aiming to also try to verify this detection and look for the global signal. It's very challenging in terms of foregrounds. You really have to characterize your foregrounds and all the systematics well to be able to constrain the cosmic signal. And then the next one is moving into interferometry, and that's the status of current interferometer experiments, which includes, as you see here, GMRT, MWA, LOFAR, and paper. Paper has been is done, and HERA, which we saw here, is the kind of next step for that collaboration. It's built next door. If you zoom on that zoom in thing, you could probably see paper in the corner.
Yeah. Okay.
Still. And so these are the current experiments. They have limits. All of them have published limits. So this chapter discusses the current status, at least the status at that time. Obviously, this is one of the chapters that's going to be dated, but it's still a nice reference for the different strategies, because all these telescopes are using different strategies to deal with foregrounds and data processing. And so this gives a nice overview of the differences that are there.
Nice.
And then finally, the future prospects, which includes what we mentioned, HERA, but also SKA phase 1 and 2, which construction should start soon, within a few months. For the SKA, which the low version that's doing the 21 centimeter is in the desert in Western Australia, which is going to be close to where MWA is currently. And then going even further, there are proposals to build dark side of the moon experiments, which would be, and some spaceborne interferometers. And this would be really cool, especially dark side of the moon. You essentially have the moon as a shield from Earth. And so you can ignore this RFI completely and go into this really, really early epoch that I mentioned, which is this dark ages. Sorry, yeah, it's for now, yeah.
For now.
I'm a huge sci-fi fan, so
Yeah.
in the books that I read, there's definitely a lot of RFI on the moon and other outer planets. So.
But currently, it's a good spot.
Currently, it's a good spot, exactly.
Very nice.
So yeah, that's it. That's the book.
Very cool. And we got 242 pages in this lovely ebook. So very nice. And for those who are interested, we'll be putting links to the videos that we showed in the description below, so you can always click on those and take a peek at those. And Andrei, I want to thank you so much for walking us through your Cosmic 21 centimeter Revolution ebook.
It's my pleasure. Thank you.
Oh, and we'll come back out in here so we get this going. All right, everyone. Thank you so much, and we'll see you on the next one. Bye-bye.
Thank you. Bye.